Yeah, so I was saying it's based on a question that Amari asked at GSI 2013, which is when a given Riemannian metric, can you tell whether or not that's a Hessian metric? And in particular, are all Riemannian metrics Hessian metrics? So asking the question in technical detail, it's just under what circumstances can we find a function f and a set of coordinates x such that the metric tensor is equal to the derivatives of f, the Hessian of f? The answer to that question, so I'll rush to the end of my talk in case I don't have enough time. In dimension 2, every metric, as long as everything's analytic, every metric, in fact, is Hessian. And that result was also proved independently by Robert Bryant, and he used Cartan-Kähler theory to prove that. And this talk is partly a bit of an advert for Cartan-Kähler theory. I'm not going to cover Cartan-Kähler theory properly, and I won't cover this particular result, in fact. I'll cover the other non-existence results, which are that in dimension 3, the general metric isn't Hessian, and that in dimensions 4 and above, there are actual restrictions on the curvature tensor of a metric for it to be a Hessian metric. And the curvature conditions, at least some of them are rather nice. Some of them are that these so-called Pontryagin forms vanish. So the Pontryagin forms, I don't think it's actually a very standard term, but the Pontryagin classes are very well known. So for surfaces, I assume most people know the Gauss-Bonnet theorem, which says that the average of the Gaussian curvature on a surface is equal to the Euler characteristic. And that gives a very fundamental connection between curvature and topology. And the Pontryagin forms, give a generalization of this. So these Pontryagin forms, they're defined in terms of the curvature tensor of a manifold, and they're closed forms that define de Rham cohomology classes, and those de Rham cohomology classes are topological invariants. So this curvature condition that these Pontryagin forms vanish is actually quite a nice curvature condition. It's not the only curvature condition. We'll show that there are more as well, but there are at least some we can identify concretely. But one of the main things I want to get across is the technique you would actually use to answer these kinds of questions. So, how can you go about systematically approaching this question, saying, have I found every curvature condition that exists, and so forth? And that comes from Cartan-Kähler theory. And I can only touch upon it, but what I want to talk about is jet bundles, which, in my understanding of Cartan-Kähler theory, underpin the subject. So let me start with a simpler question, a trivial question really, which is if we've got a metric G and we want to find a potential F such that the metric is given by the product of the first derivatives. It's a stupid question. It's a deliberately stupid question because we know that this is an n-dimensional space on an n-manifold. The space of possible metrics is order n squared. So if n's large enough, this is a stupid question. The image of the map sending a vector to the symmetric product of the vector just won't be onto. So the vast majority of metrics are clearly not of that form. And the interpretation of that is just that for a given horrible partial differential equation, you might not even be able to algebraically find a solution at a single point. Another example of a partial differential equation is, can we solve this equation for a one-form eta? Can we find a potential f such that df equals eta? Well, I hope everybody knows the answer to that, which is you can only find a solution if d eta is equal to 0. And so in this case, you can always find a solution at a point. There's nothing algebraically daft about the question. But we've got this extra condition, d eta equals 0, which we're required to even find sort of first-order solutions. And the point about Cartan-Kähler theory is very simply that you can extend this. You can look at second derivatives, and does that give algebraic conditions? Third derivatives, does that give algebraic conditions? And one applies this in a very systematic way, and you can find all obstructions to the local existence of the solution of any partial differential equation. So it's a very systematic process. And every obstruction that you find will come about essentially because of this fact that, where is it, d2f equals 0. That's an expression of the fact that partial derivatives in different directions commute. And every obstruction comes essentially from that fact. So the process of Cartan-Taylor theory is really just giving you a systematic way of taking into account the fact that derivatives commute. So we get some more technicalities now. We've just got two vector bundles, E and F, and we're just considering any differential operator from sections of the first bundle to sections of the second bundle. And we can think of D as a mapping of what's called the kth jet of E to the vector bundle F. So the kth jet of a vector bundle is just the equivalence class of sections of that vector bundle up to order k. So you consider the first k derivatives. And if the first k derivatives of your section are the same, they've got the same jet. Given a differential operator, we can define what's called its first prolongation by differentiating it. And that's a map from the k plus 1th jet bundle to the first jet bundle. And you can prolong as long as you like. So you can define the ith prolongation. And the general statement of what I was saying on the previous slide is that you can only hope to solve the equation dE equals F if you can find algebraic solutions to these prolonged equations at each point. So you can reduce the problem of, at least in the analytic category this is, you can reduce the problem of solving PDEs to just asking, does this algebraic problem have solutions? And the entire Cartan-Taylor theory tells you there's nothing else you really need to consider. So we can apply that to our particular problem of whether a given metric has a Hessian metric by just a very simple dimension counting argument. So the number of k-jets of a single function of n variables is given by this formula. It's given by the sum of the dimension of this symmetric power. That shouldn't be k plus 2, that should just be k. Sorry about that. So the reason for this is that derivatives commute. So we aren't adding up the ith tensor power, we're adding up the symmetric power. So this gives a certain growth in the size of the space of k-jets. And for the problem I want to consider for finding potentials for Hessian metrics, so we want to solve this equation, we just count the size of the space on each side. And we want to choose a function f and coordinates x. So it's an order 2 operator, so let's consider k plus 2 jets of f and x. Dimension counting, we'll get this formula here for the number of possible k plus 2 jets of a potential and a set of coordinates. You can also count the space, the number of k-jets of the metric, and we'll get this formula, all just from the previous slide. And then you just compare the size of those, and as if n is greater than 2, this one grows much more rapidly than that one. And that just tells us that there must be algebraic conditions that stop some metrics from having a given potential and coordinates. So this is a simple dimension counting argument that not all metrics are Hessian metrics. And you can say it very sloppily by saying the Riemannian metric depends on n plus 1 over 2 functions of n variables. Those are just the coordinates of gij. The Hessian metric, on the other hand, depends upon n plus 1 functions of n variables, namely the potential and your choice of coordinates. Well, n plus 1 over 2 is bigger than n plus 1. So there are far more metrics than there are Hessian metrics. It's a dodgy argument. Don't completely believe it. It's better to do it in terms of the jets because it does give you the wrong answer in dimensions 2 and 1 because you really need to take the diffeomorphism group into account when you're doing this counting. But it does mean you can fairly quickly just guess there are going to be lots more metrics than Hessian metrics. So the next stage of this is so we've shown that not all metrics are Hessian metrics, but we'd like to find out a bit more information. And I promised earlier that there are actually conditions on the curvature tensor. So I want to try and find those conditions now. And I don't even need to remind you, I don't think, because it's covered very much in the last talk, that Hessian metrics correspond to dually flat structures and vice versa. And so here's a definition of what I mean by a dually flat structure. I've got two covariant derivatives, nabla bar and nabla bar star, so I'm afraid I'm using different notation from the last talk. And they're dual in this sense, and both of those connections are flat. That's a dually flat structure. And we had this formula in the previous talk. This is even simpler, actually, than the formula from the previous talk. You can write down the curvature tensor of the Levi-Civita connection. So this is the curvature tensor of the metric in terms of the discrepancy between these two dual connections and the Levi-Civita connection. So I can't remember what letter. It wasn't A in the previous talk. It was some symmetric tensor in the previous talk. And we can write the metric in terms of this symmetric 3 tensor. And this is the key result that I use in this talk. It's just this relationship between the Riemann curvature tensor and A, a symmetric 3 tensor that relates the Levi-Civita connection to this flat connection. So we actually had the proof of this in the previous talk as well, but it's important enough that I'll just briefly state it again. The fact that this connection is torsion-free tells us that A is symmetric in the first two components. Then, using the metric to identify T star and T, using the fact that both of these are torsion-free, that tells me that A is a fully symmetric tensor. And then I just write out the definition of the curvature tensor for nabla bar. So that's one curvature tensor, but I know that's equal to 0. Expand the right-hand side out in terms of this tensor A that tells me the difference between nabla and nabla bar. I get this slightly nasty formula. And then I just use the symmetries of the curvature tensor that tell me that R lies in lambda 2, tensor lambda 2. So it's anti-symmetric on both parts. So anything which is symmetric on both parts can be cancelled, specifically this piece. So this is symmetric, that's anti-symmetric, and we get the result. So it's this fundamental relationship between the Riemann curvature tensor and A, this tensor that defines the connection. So this gives us straight away an obstruction to the existence of a Hessian metric. So if we define a map it's a quadratic map, from the space of these tensors A to the space of curvature tensors by that formula, so rho of A is equal to some funny anti-symmetrization of the tensor A, then the Riemann curvature tensor must live in the image of rho. So that's an obstruction to the existence of a Hessian metric. And it's a genuine obstruction by dimension counting. The dimension of this space is much smaller than the dimension of that space, if n is greater than or equal to 5. So there must be obstructions to a metric being a Hessian metric in dimension greater than or equal to 5. The result's slightly more interesting in dimension 4, because dimension counting would make you think that the dimension of the space of curvature tensors, so algebraic curvature tensors in dimension 4 is a 20-dimensional space, as is the space of these tensors A. So you would guess that the map would be onto, but you would guess wrong. And if you, in fact, just pick a random symmetric tensor, compute the rank of this map rho, compute the rank of its derivative, then you'd expect, at a generic point, this to equal the maximal rank. So I did this, and the rank is 18. So I deduce that, assuming I picked a random enough tensor, that the image of rho is, in fact, 18-dimensional. It's not a proof, but it's pretty clear that it's 18-dimensional. So this tells us that even in dimension 4, there are curvature obstructions to a metric being a Hessian metric. But it would be very nice to find those out rather more explicitly and to actually prove it, rather than prove it with probability 1. And the question that Amari asked me about it was, well, what can you actually say about the curvature tensor if it lives in the image of rho? I mean, can we write down some specific conditions, some equations on the curvature tensor for it to lie in the image of rho? So algebraically, we can just say it's in the image, that's an obstruction. But it'd be nice to get some pretty formulae. I think the question that's being asked is an implicitization question. So we've got a map rho, mapping some space into another space, and we're saying something lies in the image of rho. That means we're kind of giving a parametric form for a variety that we're interested in. We're saying rho is a parameterization of that space. And what we're after is an implicit formula saying, here's some algebraic equation on the variety. Can we find some nice algebraic form for that variety? And technically, this is a question from real algebraic geometry, which makes it a very intractable problem. Because generally in real algebraic geometry, you've got to turn everything turns into inequalities when you try and work out the details of, say, an implicitization problem. But if we ignore that and just complexify everything and say we've got the map rho is well defined between complex vector spaces, can we find a nice algebraic variety that describes the complexified image of rho? And then there's an algorithm for that, using Gröbner bases. And you could, in principle, apply this, put it through the machine of Gröbner bases, and it will give you a formula saying the curvature tensor applies maybe the following quadratic and the following cubic in the curvature tensor. In principle, you could apply it. I tried to apply it, and the computer never got back to me. The algorithms are extremely inefficient. So, although the question kind of makes sense of trying to find an algebraic expression satisfied by the curvature tensor, it's not very clear how to go about finding that. So, the strategy that I decided to adopt was that the space of curvature tensors is associated with some representation of the orthogonal group. And we can decompose the curvature tensor into irreducible representations under the orthogonal group. Similarly, we can decompose the symmetric power into representations. And then Shor's lemma tells you that any invariant map from one space to the other has got to be a multiple of the obvious maps coming from this decomposition. So you can actually very neatly classify, using representation theory, you can find every map of given degree from, every invariant map of given degree from one space of tensors to another. So I just very systematically went through the quadratic algebraic expressions that R might satisfy, cubic expressions it might satisfy, and so forth, just testing to see if I could prove that those relationships were satisfied. And so I managed to get this result. So the first one is a quadratic in the curvature tensor. This is all on the 4 manifold. It's only feasible on the 4 manifold. So we've got this neat quadratic that's satisfied by the curvature on a 4 manifold, and this revolting cubic, which is also satisfied. And the only proof I have of this latter equation is proof by Mathematica. You just construct a general algebraic curvature tensor, form that combination, and yeah, it gives you the answer 0. I've got no need to prove. But this one, I can generalize, because this one I recognized was the Pontryagin form of a 4 manifold. And I was at, how long have I got? 2 minutes, okay. So I've described the Pontryagin forms loosely, so they come from algebraic topology. And this formula here, this nasty polynomial in the curvature tensor, These polynomials here, they generate the Pontryagin forms. So what we do is we take the curvature tensor and we choose any symmetrization in 2p variables, and we apply it to the indices. So in the lower indices, we've got symmetrization, and then we've got lots of contractions going on diagonally. Okay. So that's the Pontryagin form. That defines the Pontryagin form. And to show they've vanished, here we are. The main trick is to rewrite these tensors A in pictorial notation. So we just represent each A as a vertex of a graph. And then we label the non-contracted vertices and join them together. So because we've got contraction here, that line represents the contraction. So we can draw pretty pictures, trivalent graphs, that represent these calculations of the tensor. And if you rewrite the curvature tensor before that we had, you get this very pretty picture. So it's some symmetrization of this picture on the curvature tensors with lots of contractions going on. And the point you can notice is that this, if you shift it left one, this looks like the same tensor, but the permutation here changes the sign of that. So this picture shows us that the Pontryagin forms vanish, and it comes essentially from the fact that the tensor A is symmetric, and so can be well represented in the trivalent graph. So that's all I wanted to say.